Hello everyone, welcome to my YouTube channel. Today we will again continue the decision tree classification. Today's session we will mainly focus on understanding all the different hyperparameters from the decision tree classifier. And why I'm focusing more on this hyperparameter, actually it is better to understand all these hyperparameters right now before you jump into different algorithms like random forest, AdaBoost, gradient boosting, XGBoost. All these algorithms will use under the hood the decision tree, and you need to do the hyperparameter tuning for all these hyperparameters, whatever available in the decision tree. So let's jump into this. Okay. So for today's session, just bear with me because I have to go through a lot of time up and down in this screen. But high level, what I'm doing, we have IRIS datasets available in sklearn, and I'm just pulling those datasets. And this dataset is very popular. You can just quickly search on a Google, and IRIS datasets has three different kinds of flowers, and it's basically doing the classification. Intention is to show how the hyperparameters are impacting the decision tree. That's the main intention in today's class, and it's very useful. I'll share this notebook, and if you just keep this handy, it will be very helpful for understanding other algorithms and their hyperparameters. Okay. So this is a very simple code where I'm just using all the x values, whatever is available here. Y values is my target variable. And then I'm calling the decision tree classifier. Random state 42, I will explain just in a couple of minutes actually. Right now, assume that we are calling a decision tree with all the default hyperparameters. We are not passing any hyperparameters, just we are running it. And if we just run this thing, we'll get a tree like this. And just keep this tree in your notebook. You'll see it's basically splitting the data such a way that you will get the pure split almost in all the places, and you'll create the leaf node for everywhere. Okay. So this is the reason, like if you just allow the decision tree to grow like this, it will create a overfit because it will read your training data, and based on that, it will create this model. But when it will go for a unseen data, it will probably not work that good actually. Okay. So if you just do the decision tree classifier I mentioned, like shift tab, we have all these different hyperparameters. Okay. Now we'll go one by one and we'll show the example. For the time being, I'm not going in depth of the criteria because I mentioned so many times that mainly we have Gini impurity and entropy, these two process by which we basically try to identify the impurity of a split. So that's why I'm not giving any specific examples on this one, but it's basically when we do the hyperparameter tuning, either we pass both of them and let it decide which one is the right one. Splitter is again is a strategy to use to choose the split at each node. Normally, like when I gave the example, we selected the splitter equal to best. Best strategy select the best split based on the choose criteria, while the random selects the random splits. Okay, now coming to the max depth, which probably very useful hyperparameter. When it is the default value is none, what does it mean? If it is none, what it will do, it will just create the tree exactly like this. It will just keep on growing as long as it's not creating all the leaf nodes. How we can control it? So if we pass a value like 3, what will happen? This tree will not grow entirely. It will just grow up to the third level. You see, up to the third level. So if I just try to minimize, probably it will not. 1, 0, 1, 2, and 3. Make sense? It's starting from the 0th level. Okay. So max depth equal to 3 is like this way it works. What is the next one? So next one is basically our mean sample split. Now mean sample split. What does it mean? It's mean the minimum number of samples required to split an internal node. By default, it is 2. As long as you have 2 samples, it will try to split. But, and all these things I'm talking about from the binary point of view. Okay. So for example, like if right now my intention is, okay, let me just try with minimum sample splits equal to 50. What does it mean? If I have a node where my number of samples are less than 50, then I will not do any more splitting. So what will happen? Like, look here. It's exactly like this. It got stopped here because it has a 50, sample 50. It has sample more than 50, so it's got splitted again. Samples 54 and 46, so it is not splitted. 54, so it's got splitted. And that's another way I'm doing the pruning. Everything is actually whatever all these parameters are helping to basically reduce the overfitting. Intention in today's class is just to explain all these parameters, how it's working under the hood. But definitely in a real life, when you will work, you have to rely on grid search CV or hyperparameter tuning actually, because you have to pass all the different values and a lot of combinations, and then you have to find out the best parameters. Okay. So the next one is minimum samples leaf. Again, here what I'm doing, I'm just passing. You can just run this code. I can give you this notebook and you can just run this code as it is. You'll understand each of these things very properly actually. But what is this? Minimum sample leaves. The minimum number of samples required to be a leaf node. Minimum samples leaf by default is 1. So each leaf node must have at least one sample, right? That's our default, but we can control it. We can say, no, if I have minimum 5, then also I can consider that is a leaf node. And if I just run this, like what will happen? Like, let's see. So it will split, but look here, I have minimum samples as 6. So I'll just consider this as the leaf nodes and I'll just stop it here. Sample is 5. I'll just stop it here. I'll not do any more splitting. I found it, so it's done. Clear? I think up to this. Again, I'm just going up, just making sure it's following the same path. Okay. So next is minimum sample leaves and then minimum weight fraction leaf. This is again important. The minimum weighted fraction of the sum of weights required to be a leaf node. Again, by default, it's 0, 0. But if this value can lies between 0 to 0.5, and what exactly it's mean, the minimum weighted fraction of the sum of weights required to be a leaf node. If I just run it, what will happen, and then you'll understand. So look at this, because it's a multi-class classification, and if I just check the ratio here, it's 0.5 because 25 by 50, 25 by 50. So that's why it got stopped here. Clear? Think up to this. Minimum weighted fraction leaf is cleared. Next is the random state. Again, the random state is used for reproducibility of the decision tree model. That's why from the very beginning I was using that random state equal to 42, because in that case, if you run tomorrow, you just take this notebook and run this, it will produce the exact same result. That's the reason we use this random state. So this is exactly helpful, like when you have to reproduce the same results, run multiple times. It's always recommended to use a random state. Max leaf nodes. Max leaf nodes. Right now, the maximum number of leaf nodes allowed in the decision tree. The maximum number of leaf nodes allowed in the decision tree. None mean right now its default is none. If max is none, there is no maximum limit on the number of leaf nodes. But if I put number of leaf nodes is 4, that's mean if I just run it, it will create only 4 nodes. Look, one leaf node, second leaf node, third leaf node, and fourth leaf node, and it got stopped. The way once it's find all the 4 leaf nodes and it stopped. Minimum impurity decrease. A node will be split if the split induced a decrease of the impurity greater than or equal to minimum impurity decrease. Example, minimum impurity decrease 0, 0 by default is set to 0, meaning its split will only be considered if they reduced in a decrease in impurity. Okay. So what does it mean? Like if I put a value like 0.1, then it will get calculated based on that value. It will take a decision and it will just build the tree up to that level. After that, it will not build. So that's very important. Okay. And if you compare with our original version, you can see that after this, our values are actually um, greater than this, so it's not doing any more split, and this is the way it stopped. Okay. Minimum purity split, again, this one is deprecated, so I'm not trying to explain this. This is not, I think, not at all needed, because this is actually deprecated in sklearn, but I just show you that it is deprecated. You don't need to think about this one. Okay, so I'll not try to explain this one. Class weight. This is, I think, it's very important. And let me explain why it's very important. Because in the practical life, when you will work, the data will not be always balanced. And I think right now, kind of, you got some idea that what is balanced and what is imbalanced data. But if you have a positive class of 100 records and the negative class or has 900 records, that's kind of a imbalance ratio, right? So that's where we called it imbalanced. So let's see, what is the definition? Definition is weights associated with classes in the form. Example, class weights equal to none. By default, it is set to none, meaning all classes are given equal weights. Positive class, negative class, 1, 0, all is given as a equal weights, and that is okay if your data is not imbalanced. If your data is imbalanced, then let me just give you one example. Then that is the time when you should use this, and it's very important that time. For example, a binary classification problem. We have two classes, class 0 as 100 sample, class 1, 1000 samples. So you will basically do the class frequency, then you will calculate the inverse of the class frequency, and then we use those values into the class weight. So that's the way we can use this parameter, and this is very, very handy parameter if your data is imbalanced. When I will really work with the imbalanced data sets, I will show you some practical example also. But remember right now, this parameter, this hyperparameter is giving very good value if your data is imbalanced and it is trying to make the better result. CCP hyphen alpha, this is the definition, is complexity parameter used for minimal cost complexity pruning. Now, this hyperparameter is little confusing when you try to think about max depth and CCP alpha. So that's why I give a little bit of descriptions here, like what the max depth is doing. Both are kind of this line probably helpful. It is common to use either max depth or CCP alpha to control the complexity of the decision tree because both are actually helping in the pruning. I personally, like I worked in a company, I personally never really used both of them together. Um, but again, based on your example, based on your scenario, you have to probably take the decision whether you have to use both the hyperparameters or use one single hyperparameter. That's all because there will be always a trade-off. So it's better to use both of them and let do the grid search CV kind of check whether you're getting a better result, better parameters or something like that. But I hope this will help you to understand, this notebook will help you to understand all the different hyperparameters, whatever available for the decision tree. And it's crucial to understand all these things because all these things you have to pass and you have to play and you have to find out the best hyperparameter for random forest, ADA boost, gradient boosting, XG boost, for any kind of algorithms you have to do these things. So it's important to understand this thing. And thank you so much for following the class and really appreciate your support. If you like it, please give a thumbs up or subscribe my channel. I will come out with more such videos very soon. Thank you so much. Have a nice day. Bye.